This is a photo of change, a set of keys in a pile. There appear to be 5 pennies, 3 quarters, 4 dimes, and 2 nickels. The key ring has a bronze whale on it and holds 11 keys, figure 7. 1. If you want to figure out the distribution of the change people carry in their pockets, using the central limit theorem and assuming your sample is large enough, you will find that the distribution is the normal probability density function. Credit Modification of Work American Coins by Paula R. Lively Flickr, CC by 20. Why are we so concerned with means? 2 reasons are. They give us a middle ground for comparison and they are easy to calculate. In this chapter, you will study means and the central limit theorem. The central limit theorem is one of the most powerful and useful ideas in all of statistics. The central limit theorem is a theorem, which means that it is not a theory or just somebody's idea of the way things work. As a theorem, it ranks with the Pythagorean theorem, or the theorem that tells us that the sum of the angles of a triangle must add to 180. These are facts of the ways of the world rigorously demonstrated with mathematical precision and logic. As we will see, this powerful theorem will determine just what we can and cannot say in inferential statistics. The central limit theorem is concerned with drawing finite samples of size n from a population with a known mean mu and a known standard deviation sigma. The conclusion is that if we collect samples of size n with a large enough n, calculate each sample's mean, and create a histogram distribution of those means, then the resulting distribution will tend to have an approximate normal distribution. The astounding result is that it does not matter what the distribution of the original population is, or whether you even need to know it. The important fact is that the distribution of sample means tend to follow the normal distribution. The size of the sample, n, that is required in order to be large enough, depends on the original population from which the samples are drawn. The sample size should be at least 30 or the data should come from a normal distribution. If the original population is far from normal, then more observations are needed for the sample means. Sampling is done randomly and with replacement in the theoretical model. The sampling distribution is a theoretical distribution. It is created by taking many samples of size n from a population. Each sample mean is then treated like a single observation of this new distribution, the sampling distribution. The genius of thinking this way is that it recognizes that when we sample, we are creating an observation, and that observation must come from some particular distribution. The central limit theorem answers the question. From what distribution did a sample mean come? If this is discovered, then we can treat a sample mean just like any other observation and calculate probabilities about what values it might take on. We have effectively moved from the world of statistics, where we know only what we have from the sample, to the world of probability, where we know the distribution from which the sample mean came and the parameters of that distribution. The reasons that one samples a population are obvious. The time and expense of checking every invoice to determine its validity or every shipment to see if it contains all the items may well exceed the cost of errors in billing or shipping. For some products, sampling would require destroying them, called destructive sampling. One such example is measuring the ability of a metal to withstand saltwater corrosion for parts on ocean-going vessels. Sampling thus raises an important question: just which sample was drawn. Even if the sample were randomly drawn, there are theoretically an almost infinite number of samples. With just 100 items, there are more than 75 million unique samples of size 5 that can be drawn. If 6 are in the sample, the number of possible samples increases to just more than 1 billion. Of the 75 million possible samples, then, which one did you get? If there is variation in the items to be sampled, there will be variation in the samples. One could draw an unlucky sample and make very wrong conclusions concerning the population. This recognition that any sample we draw is really only one from a distribution of samples provides us with what is probably the single most important theorem in statistics, the central limit theorem. Without the central limit theorem, it would be impossible to proceed to inferential statistics from simple probability theory. In its most basic form, the central limit theorem states that regardless of the underlying probability density function of the population data, the theoretical distribution of the means of samples from the population will be normally distributed. In essence, this says that the mean of a sample should be treated like an observation drawn from a normal distribution. The central limit theorem only holds if the sample size is large enough, which has been shown to be only 30 observations or more. Figure 7.2 graphically displays this very important proposition. Figure 7.2, notice that the horizontal axis in the top panel is labeled x. These are the individual observations of the population. This is the unknown distribution of the population values. The graph is purposefully drawn all squiggly to show that it does not matter just how oddball it really is. Remember, we will never know what this distribution looks like, or its mean or standard deviation for that matter. The horizontal axis in the bottom panel is labeled XS. This is the theoretical distribution called the sampling distribution of the means. Each observation on this distribution is a sample mean. All these sample means were calculated from individual samples with the same sample size. The theoretical sampling distribution contains all of the sample mean values from all the possible samples that could have been taken from the population. Of course, no one would ever actually take all of these samples, but if they did, this is how they would look. And the central limit theorem says that they will be normally distributed. The central limit theorem goes even further and tells us the mean and standard deviation of this theoretical distribution. Parameter population distribution sample sampling distribution of x mean mu, x letter 1d707, x and e letter 1d707, x equals letter 1d707 standard deviation sigma s letter 1d70e, x equals letter 1d70e square root letter 1d45b table 7. 1. The practical significance of the central limit theorem is that now we can compute probabilities for drawing a sample mean, x, in just the same way as we did for drawing specific observations, x's, when we knew the population mean and standard deviation and that the population data were normally distributed. The standardizing formula has to be amended to recognize that the mean and standard deviation of the sampling distribution, sometimes called the standard error of the mean, are different from those of the population distribution, but otherwise nothing has changed. The new standardizing formula is letter 1d44d equals x minus letter 1d707, x letter 1d70e x equals x minus letter 1d707 letter 1d70e square root letter 1d45b. Notice that micro x in the first formula has been changed to simply micro in the second version. The reason is that mathematically it can be shown that the expected value of micro x is equal to micro. This was stated in table 7.1 above. Mathematically, the x symbol read the expected value of x. This formula will be used in the next unit to provide estimates of the unknown population parameter mu. The law of large numbers, along with the central limit theorem, provides another critical piece of information to allow us to engage in inferential statistics. In short, the law of large numbers proves that the expected value of the sampling distribution of the sample mean is the population mean. Letter 1d438, letter 1d707 x equals letter 1d707. The proof is through the concept of large numbers. Suppose you were to take a sample and calculate a sample mean. Then you take another sample, combine it with the previous sample, and calculate the sample mean of the combined sample. Then you repeat this process over and over, creating bigger and bigger samples and calculating a sample mean each time along the way. The sample means from larger and larger samples will get closer and closer to the population mean mu. Figure 7.3 shows the running average as more sample means are added and then averaged. The proof of the law of large numbers mathematically was perfected during a period of 20 years and was presented by Jacob Bernoulli in 1713. Figure 7.3 stated mathematically lim letter 1d45b right infinity letter 1d443. X letter 1d45b minus letter 1d707. Letter 1d700 equals 0 or alternatively presented as letter 1d443. Lim letter 1d45b right infinity. X letter 1d45b equals letter 1d707 letter 1d700 equals 1 where xn is the running average as additional sample means are added. The previous sample means. In summary, there are three critical mathematical conclusions that flow from the central limit theorem and the application of the law of large numbers. By the central limit theorem, for large enough sample sizes, the sampling distribution of sample means tends to be normally distributed regardless of the underlying distribution of the population data. As the sample size n gets larger and larger, the sampling distribution standard deviation gets smaller. Remember that the standard deviation for the sampling distribution of xn is letter 1d70e square root letter 1d45b. The sample mean x is more likely to be closer to mu as n increases. By the law of large numbers, the expected value of the sampling distribution of the sample mean is the population mean. Law of large numbers. The law of large numbers says that if you take samples of larger and larger size from any population, then the mean of the sampling distribution, letter 1d707, x tends to get closer and closer to the true population mean mu. From the central limit theorem, we know that as n gets larger and larger, the sample means follow a normal distribution. The larger n gets, the smaller the standard deviation of the sampling distribution gets. Remember that the standard deviation for the sampling distribution of x is letter 1d70e square root letter 1d45b. This means that the sample mean x must be closer to the population mean mu as n increases. We can say that mu is the value that the sample means approach as n gets larger. The central limit theorem illustrates the law of large numbers. Examples of the central limit theorem, this concept is so important and plays such a critical role in what follows it deserves to be developed further. Indeed, there are two critical issues that flow from the central limit theorem and the application of the law of large numbers to it. These are the probability density function of the sampling distribution of means is normally distributed regardless of the underlying distribution of the population observations, and standard deviation of the sampling distribution decreases as the size of the samples that were used to calculate the means for the sampling distribution increases. Taking these in order, it would seem counterintuitive that the population may have any distribution and the distribution of means coming from it would be normally distributed. With the use of computers, experiments can be simulated that show the process by which the sampling distribution changes as the sample size is increased. These simulations show visually the results of the mathematical proof of the central limit theorem. Here are three examples of very different population distributions and the evolution of the sampling distribution to a normal distribution as the sample size increases. The top panel in these cases represents the histogram for the original data. The three panels show the histograms for 1,000 randomly drawn samples for different sample sizes. N equals 10, N equals 25, and N equals 50. As the sample size increases and the number of samples taken remains constant, the distribution of the 1,000 sample means becomes closer to the smooth line that represents the normal distribution. Figure 7.4 is for a normal distribution of individual observations, and we would expect the sampling distribution to converge on the normal quickly. The results show this and show that even at a very small sample size the distribution is close to the normal distribution. Figure 7.4 Figure 7.5 is a uniform distribution which, a bit amazingly, quickly approached the normal distribution even with only a sample of 10. Figure 7.5 Figure 7.6 is a skewed distribution. This last one could be an exponential, geometric, or binomial with a small probability of success creating the skew in the distribution. For skewed distributions, our intuition would say that this will take larger sample sizes to move to a normal distribution, and indeed that is what we observe from the simulation. Nevertheless, at a sample size of 50, not considered a very large sample, the distribution of sample means has very decidedly gained the shape of the normal distribution. Figure 7.6 The central limit theorem provides more than the proof that the sampling distribution of means is normally distributed. It also provides us with the mean and standard deviation of this distribution. Further, as discussed above, the expected value of the mean, μx, is equal to the mean of the population of the original data, which is what we are interested in estimating from the sample we took. We have already inserted this conclusion of the central limit theorem into the formula we use for standardizing from the sampling distribution to the standard normal distribution. And finally, the central limit theorem has also provided the standard deviation of the sampling distribution, letter 1d70e, x equals letter 1d70e square root letter 1d45b. And this is critical to have to calculate probabilities of values of the new random variable, x. Figure 7.7 shows a sampling distribution. The mean has been marked on the horizontal axis of the x, and the standard deviation has been written to the right above the distribution. Notice that the standard deviation of the sampling distribution is the original standard deviation of the population, divided by the sample size. We have already seen that as the sample size increases, the sampling distribution becomes closer and closer to the normal distribution. As this happens, the standard deviation of the sampling distribution changes in another way. The standard deviation decreases as n increases. At very large n, the standard deviation of the sampling distribution becomes very small, and at infinity it collapses on top of the population mean. This is what it means that the expected value of micro x is the population mean micro. Figure 7.7 at non-extreme values of n, this relationship between the standard deviation of the sampling distribution and the sample size plays a very important part in our ability to estimate the parameters we are interested in. Figure 7.8 shows three sampling distributions. The only change that was made is the sample size that was used to get the sample means for each distribution. As the sample size increases, n goes from 10 to 30 to 50, the standard deviations of the respective sampling distributions decrease because the sample size is in the denominator of the standard deviations of the sampling distributions. Figure 7.8 The implications for this are very important. Figure 7.9 shows the effect of the sample size on the confidence we will have in our estimates. These are two sampling distributions from the same population. One sampling distribution was created with samples of size 10 and the other with samples of size 50. All other things constant, the sampling distribution with sample size 50 has a smaller standard deviation that causes the graph to be higher and narrower. The important effect of this is that for the same probability of one standard deviation from the mean, this distribution covers much less of a range of possible values than the other distribution. One standard deviation is marked on the x-axis for each distribution. This is shown by the two arrows that are plus or minus one standard deviation for each distribution. If the probability that the true mean is one standard deviation away from the mean, then for the sampling distribution with the smaller sample size, the possible range of values is much greater. A simple question is, would you rather have a sample mean from the narrow, tight distribution or the flat, wide distribution as the estimate of the population mean? Your answer tells us why people intuitively will always choose data from a large sample rather than a small sample. The sample mean they are getting is coming from a more compact distribution. This concept will be the foundation for what will be called level of confidence in the next unit, Figure 7.9. The central limit theorem tells us that the point estimate for the sample mean, x, comes from a normal distribution of xs. This theoretical distribution is called the sampling distribution of x. Yes, we now investigate the sampling distribution for another important parameter we wish to estimate, p from the binomial probability density function. If the random variable is discrete, such as for categorical data, then the parameter we wish to estimate is the population proportion. This is, of course, the probability of drawing a success in any one random draw. Unlike the case just discussed for a continuous random variable, where we did not know the population distribution of x's, here we actually know the underlying probability density function for these data. It is the binomial distribution. The random variable is x equals the number of successes and the parameter we wish to know is p, the probability of drawing a success, which is of course the proportion of successes in the population. The question at issue is, from what distribution was the sample proportion p equals xn drawn? The sample size is n and x is the number of successes found in that sample. This is a parallel question that was just answered by the central limit theorem. From what distribution was the sample mean, x, drawn? We saw that once we knew that the distribution was the normal distribution, then we were able to create confidence intervals for the population parameter micro. We will also use this same information to test hypotheses about the population mean later. We wish now to be able to develop confidence intervals for the population parameter p from the binomial probability density function. In order to find the distribution from which sample proportions come, we need to develop the sampling distribution of sample proportions, just as we did for sample means. So again, imagine that we randomly sample, say, 50 people and ask them if they support the new school bond issue. From this, we find a sample proportion p and graph it on the axis of p's. We do this again and again, etc. etc. until we have the theoretical distribution of p's. Some sample proportions will show high favorability toward the bond issue, and others will show low favorability because random sampling will reflect the variation of views within the population. What we have done can be seen in Figure 7.10. The top panel is the population distributions of probabilities for each possible value of the random variable x. While we do not know what the specific distribution looks like because we do not know p, the population parameter, we do know that it must look something like this. In reality, we do not know either the mean or the standard deviation of this population distribution, the same difficulty we faced when analyzing the x's previously. This is a normal distribution curve. The peak of the curve coincides with the point 7200 on the horizontal axis. The point 7500 is also labeled. A vertical line extends from point 7500 to the curve. The area to the right of 7500 below the curve is shaded. Figure 7.10. Figure 7.10 places the mean on the distribution of population probabilities as micro equals letter 1 d45b letter 1 d45d, but of course we do not actually know the population mean because we do not know the population probability of success. Below the distribution of the population values is the sampling distribution of p. S. Again, the central limit theorem tells us that this distribution is normally distributed, just like the case of the sampling distribution for xs. This sampling distribution also has a mean, the mean of the piece, and a standard deviation, letter 1d70, letter 1d45d. Importantly, in the case of the analysis of the distribution of sample means, the central limit theorem told us the expected value of the mean of the sample means in the sampling distribution, and the standard deviation of the sampling distribution. Again, the central limit theorem provides this information for the sampling distribution for proportions. The answers are, the expected value of the mean of sampling distribution of sample proportions, micro p, is the population proportion p. The standard deviation of the sampling distribution of sample proportions, letter 1D70EP, is the population standard deviation divided by the square root of the sample size, n. Both these conclusions are the same as we found for the sampling distribution for sample means. However, in this case, because the mean and standard deviation of the binomial distribution both rely upon p, the formula for the standard deviation of the sampling distribution requires algebraic manipulation to be useful. We will take that up in the next chapter. The proof of these important conclusions from the central limit theorem is provided below. Letter 1D438, letter 1D45D equals letter 1D438, xn equals 1n letter 1D438, letter 1D465 equals 1n letter 1D45b letter 1D45D equals letter 1D45D, the expected value of x. Ex is simply the mean of the binomial distribution, which we know to be np. Letter 1D70ep2 equals var, letter 1D45D equals var, xn equals 1 and 2 var. 1 and 2 letter 1D45b letter 1D45D 1 minus letter 1D45D equals letter 1D45D 1 minus letter 1D45D. And the standard deviation of the sampling distribution for proportions is thus. Letter 1D70EP equals square letter 1D45D 1 minus letter 1D443. And parameter population distribution sampling distribution of p's mean micro equals npp equals xnp. And EP equals P standard deviation letter 1D70E equals square letter 1D45B letter 1D45D letter 1D45E letter 1D70EP equals square. Letter 1D45D 1 minus letter 1D45D in Table 7. Table 7.2 summarizes these results and shows the relationship between the population, sample, and sampling distribution. Notice the parallel between this table and Table 7. One for the case where the random variable is continuous, and we were developing the sampling distribution for means. Reviewing the formula for the standard deviation of the sampling distribution for proportions, we see that as n increases, the standard deviation decreases. This is the same observation we made for the standard deviation for the sampling distribution for means. Again, as the sample size increases, the point estimate for either micro or p is found to come from a distribution with a narrower and narrower distribution. We concluded that with a given level of probability, the range from which the point estimate comes is smaller as the sample size, n, increases. Figure 7.8 shows this result for the case of sample means. Simply substitute p for x, and we can see the impact of the sample size on the estimate of the sample proportion. We saw that the sample size has an important effect on the variance, and thus the standard deviation of the sampling distribution. Also of interest is the proportion of the total population that has been sampled. We have assumed that the population is extremely large and that we have sampled a small part of the population. As the population becomes smaller and we sample a larger number of observations, the sample observations are not independent of each other. To correct for the impact of this, the finite correction factor can be used to adjust the variance of the sampling distribution. It is appropriate when more than 5% of the population is being sampled and the population has a known population size. There are cases when the population is known, and therefore the correction factor must be applied. The issue arises for both the sampling distribution of the means and the sampling distribution of proportions. The finite population correction factor for the variance of the means shown in the standardizing formula is letter 1d44d equals x minus micro letter 1d70e square root letter 1d45b square root letter 1d441 minus letter 1d45b letter 1d441 minus 1, and for the variance of proportions is letter 1d70ep equals square letter 1d45d 1 minus letter 1d45d n times square letter 1d441 minus letter 1d45b letter 1d441 minus 1. The following examples show how to apply the factor. Sampling variances get adjusted using the above formula. Example 7.1. It is learned that the population of white German shepherds in the USA is 4,000 dogs, and the mean weight for German shepherds is 45 pounds. It is also learned that the population standard deviation is 37 pounds. Problem: if the sample size is 225 dogs, then find the probability that a sample will have a mean that differs from the true probability mean by less than 2 pounds. Solution: n equals 4,000, n equals 225, letter 1d70e equals 10. 37 micro equals 75. 45 x minus micro equals plus 2 letter 1d44d equals x minus micro letter 1d70e square root letter 1d45b square root letter 1d441 minus n letter 1d441 minus 1 equals plus or minus 210. 37 square root 4,000 minus 225 4,000 minus 1 approximately 2. 978 letter 1d453 letter 1d44d approximately 2. 978 2 equals 0. 997 note that differs by less references the area on both sides of the mean within 2 pounds right or left. Try it 7. 1 for the 5,000 students in University A, the average height of the students is 170 cm. The population standard deviation is 5 cm. If the sample size is 100 students, find the probability that the sample mean is within 1 cm of the true mean. Example 7.2 When a customer places an order with Ruddy's Online Office Supplies, a computerized accounting information system, AIS, automatically checks to see if the customer has exceeded their credit limit. Past records indicate that the probability of customers exceeding their credit limit is 6. Problem Suppose that on a given day, 3,000 orders are placed in total. If we randomly select 360 orders, what is the probability that between 10 and 20 customers will exceed their credit limit? Solution n equals 3000, n equals 360, p equals 0. 6 letter 1d 70 p equals square letter 1d 45d, 1 minus letter 1d 45d. N times square letter 1d 441 minus letter 1d 45b, letter 1d 441 minus 1 equals square 0. 0, 6, 1 minus 0, 6. 360 times square 3000 minus 360 3000 minus 1 equals 0. 117 letter 1d 45d 1 equals 10 360 equals 0. 0 278 letter 1d 45d 2 equals 20 360 equals 0. 556 letter 1d 44d equals letter 1d 45d minus letter 1d 45d square root letter 1d 45d. 1 minus letter 1d 45d. N square root letter 1d 441 minus letter 1d 45b letter 1d 441 minus 1 equals 0. 0 278 minus 0, 60. 11,744 equals minus 2. 74 letter 1d 44d equals letter 1d 45d minus letter 1d 45d square root letter 1d 45d. 1 minus letter 1d 45d. N square root letter 1d 441 minus letter 1d 45b letter 1d 441 minus 1 equals 0. 0 556 minus 0, 60. 11,744 equals minus 0. 38 letter 1d 45d 0. 0 278 minus 0, 60. 11,744 letter 1d 4670. 0 556 minus 0, 60. 11,744 equals letter 1d 45d minus 2. 74 letter 1d 467 minus 0. 38 equals 0. 4,969 minus 0. 1,480 equals 0. 3489 Try it 7.2 There is a 0. 1 probability that a student gets food poisoning eating food in a cafeteria. Suppose there are 2,000 orders in a day in the cafeteria. If we select 200 orders randomly, what is the probability that between 5 and 10 students will get food poisoning?